Well, we don't have much to discuss this week because we only have 2 lectures. It's all about the inverse functions. We need to discuss with you formal tests which ensure that inverse exists. They resemble a lot tests from the first year. The only difference is that there will be some metrics flavor to these tests. But in principle, they are identical. So I'm going to go through the slides with maybe some diversions to the dynamic slides. I'm not sure yet. I don't know. This first one just tells you a few instances where we, just by the look of the graph, we can see whether inverse exists or whether it doesn't. But basically, what it brings in our heads is just the test for the inverse from the first year. So from the first year, for the inverse to exist, we need continuity and we need non-zero. We need the derivative to be non-zero. So, for instance, here on this third picture, they don't have inverse because the derivative here is 0. We have a horizontal tangent line. Here we have discontinuity. Again, we don't have the inverse. I mean, when I say we don't have the inverse, I mean we don't have around the point C. That's a very good case where we do have the inverse around any point. Here we do have the inverse except the point C where the derivative is also 0, is again 0, and that's the test or failed test for the inverse. So that's the result from the first year. A test for the inverse to exist. But now listen to what it says. It says that if you want a function, if you want to make sure that the function is invertible and the inverse function is differentiable, that's the main thing you have to look for. That's the function must have non-zero derivative in the point. If it does, then around in the vicinity of that point there will be an inverse function. We never expect the inverse to exist globally, like across the whole real line. We don't need that, and we never expect that. Inverse function theorem, it's a local result. It's a result which ensures existence of an inverse near some point. And the point for which this works, the test for that point, is the derivative being non-zero. That's what we know from the first year. And we also have the formula for that derivative. I mean, we also have the formula for the derivative of the inverse function, sorry. And here it is. Now I'd like to discuss with you what happens when you have a function of several variables. That's right. Well, the slides actually try to make the analogy, I mean, because the logic, which explains what happens in case of, say, 2 or more than 2 variables, it is linked to affine approximations. And to explain this logic slide, this slide tries to explain this logic again with the function of 1 variable. So if you take, well, it says affine function, and the affine in this place just means the same as linear. You can put the equal sign between these 2 words, affine and linear. If you take a linear function or a affine function, in one-dimensional one, it's as simple as this, mx plus b. If you ask yourself whether you can invert such a function, the answer to that will be, obviously, if the function is horizontal line, there is no inverse, but as soon as you have some non-zero slope, as soon as the m is non-zero, you can present an inverse. It's a very direct resolution. You can solve for x in this equation. If m is non-zero, if you have non-zero slope, then you can solve for x. That's a solution right here. If you now just do the renaming, you rename your x as a new dependable variable, and t of x will be now independent variable. That's the renaming. That's the formula for the inverse. Okay? So, and the inverse itself, the derivative of that inverse linear function is the m inverse, you see? If you think that this t was originally some affine approximation to a function, then this slide sort of suggests that we can link the invertibility of a function to invertibility of the affine approximation. Because the invertibility of this affine approximation is this test. But in case t is the affine approximation, this m will be exactly the derivative of the original f. That's how we build affine approximations. And that's the main idea which explains, which suggests what happens in the higher dimensions. We take affine approximation to the function of multiple variables. And we see if the affine approximation is invertible, and if it is, then the associated function is also invertible. So first we, like at the slide, discuss what happens when you take, so that's what I said here. So if your t was the affine approximation to f, then your m, it is the f dash of x at the point where you computed your affine approximation. And that's why from this line you can see that this line suggests the choice for the formula for the derivative of the inverse function. Yeah. Well, that's the same computation in case you have linear map of n variables. If you have a linear map T, both phase from Rn to Rn, all those linear affine maps, they all given by, actually I think I misled you a little bit. When I said when you put the equal sign between linear and affine, that wasn't really entirely correct. Normally when people say affine, they allow this constant term present. So when you say linear map in higher dimensions, it's just the term linear, it has this dual interpretation. For one dimensions, you know it from the school, you call this function linear. But in the higher dimensions, from the first year, you know very well that linear maps are those which are just matrix times x. There's no any constant term there present. So term linear in higher dimensions, it has a more rigid interpretation in comparison to the one dimension, where it's just because this language was heavily used in the high school. That's why we have to live with that, and we allow linear to mean both mx and mx plus b. Whereas in higher dimensions, we no longer allow this loose term linear to be as loose as this. In higher dimensions, linear is always Lx, and that's it, no b. When you bring b in, for that we have a special name, affine. That's the in higher dimensions, the difference between these two terms, affine and linear. Right, so if you have a affine map, and now I no longer can say linear because for higher dimensions linear, it's a very rigid term. It's attached only to the matrix multiplication type of map with no constant terms. Then again, we know very well from the first year what we need to do to invert such a map. It's again a solution, direct solution of x in terms of t of x. Even though this time when you do this solution, you would need to use inverse matrix to L rather than just inverse to number m. You would need to invert the matrix L. And here's my test. If my matrix is invertible, which we know how to test for that, it's a determinant test, one of the tests. The other one is a row echelon form test. Then you can invert a affine map, not linear, affine map, by directly solving for x. That's my direct solution. I just take this identity, multiply by L inverse, left-hand side, right-hand side. That's how it come up, and take b on the other side. Now I just rename these symbols. X now is my dependable variable. That's why I call it like that. This becomes independent variable, x, and that's my inverse map for my original affine map. Curiously enough, the inverse is also affine, isn't it? It's the matrix multiplication plus some constant term. Now we can just employ the same logic as I tried to explain on the slide before. If we believe in this claim that the function now, any function, is invertible if and only if the affine approximation to that function is invertible, then we can just present the result which we need. We can present a test. Look at this. We can say if t was some approximation to a function, then if we just believe in this idea that function is invertible if and only if its approximation is invertible, then here's a test again. That's the test we need. The only extra thing I have to say is that this time this L matrix, it's no longer some matrix. It is the Jacobian. It is this derivative of my map which appears in the best affine approximation. And here it is. So my test for the function to be invertible, function from Rn to Rn, interestingly enough, we have the same number of variables on the domain and the codomain, and that's it's not accidental. You can even see that by the fact that if you have different number of variables, this L matrix will no longer be square, and non-square matrices are never invertible, aren't they? We can never invert non-square metrics. So affine maps between different dimensions, they're never invertible. And by implication, if you take the functions now, if you believe again in this connection, that everything in terms of invertibility for the function is the same as for the affine approximation to that function, then functions between different dimensions never invertible. Well, that's what we expect. We would hope to expect that the function is invertible if and only if the Jacobian or derivative of that function at the point is invertible as a matrix. And that is going to be our test. So that's the result. Now framed as a theorem. The main idea behind this theorem, I just explained it to you. I tried to explain it to you. The rest is just technicalities. We're not going to go into the technicalities. But the result is this. Function between Rn and Rn, or function which lives on some domain in Rn, which is C1. One of you asked me the other day what's the C1 is. It means once continuously differentiable. So every partial derivative exists in continuous function, which means that Jacobian is well defined, and we can play with that Jacobian. So function is invertible at some point. Function, yeah, that's right. Function is invertible at some point when, if you compute the Jacobian at that point, it is invertible matrix. If it is so, then the function will be invertible. The theorem itself doesn't give you the way to find the inverse function. It doesn't give you it doesn't promise you it will be easy to find that function, but it promises you that if you if you invest enough effort, you will find it, or somebody else will find it for you. Yes. I didn't catch that. Say again. I'm sorry, I didn't catch that again.
So omega.
Omega, yeah.
Can that be Rn?
Yes, it can. Yeah, it can be Rn. So when people say something like this, when you have like a function lives on a domain in Rn, it includes the domain being the whole Rn. Yes, it just often happens function never lives on the whole Rn. There will be some division by zero. There will be some log tangent inside, which will throw some points out. Sorry. Thank you. Right. So there are a few examples how this theorem works. In fact, we had one example earlier when we used this the inverse function and derivative, and how to find the derivative of the inverse, I should say map rather than function. And I'll bring that example again just to show you now this explicitly. We'll just say like if it looks like they will have a few it looks like you will have a few questions where you would need to find the best affine approximation to the inverse map. And if you've done a few questions like so already, right? I think so, yes. If you've done so, you know that when you go for the best affine approximation, you need the Jacobian of the map. In case of the inverse map, the Jacobian of the map will be inverse matrix of the Jacobian of the original map. So this last line just make this explicit, that it is very often you will need this identity to solve a few questions in a tutorial. And I was looking for the slides. There are a few slides with examples where this formula is used as well. Okay. Any questions, please? Right. So the first example is the polar map, and that's the example I was talking about, because we have inverted polar map already with you. And when I say we have inverted it, we found the derivatives of the inverse. We haven't actually found the formula for the inverse polar map, but derivatives we used. Remember that example with the Laplacian, and when we try to find the formula for the Laplacian in the polar coordinates, we use Maple for that quite extensively. Well, now we just bring some firm basement under that question, because when I said let's just take the inverse, I never really questioned whether such an inverse exists. I just said let's just take it. And now we're going to see that actually that step, when we took the inverse polar, it was a legitimate step. That's the slide which shows that. So if you have a polar map, Where's my pointer? Yes. That's a polar map in scalar form. Effectively, it takes R2 to R2, or domain in R2, because actually R never goes negative here. So that's the vector form of your polar map. R theta vector taken to xy vector. And as a matter of fact, like I said, R2 here, not supposed to, I mean, strictly speaking, you have to put an omega here because this function lives only for positive r's, or 0, and only for theta between negative pi and pi. For the others, this function, I mean, we don't really consider that function for the other pairs of r and theta. So if you want to test whether this function is invertible, you need to run this test for the determinant. You compute the Jacobian of this map. That's a Jacobian, x by r, x by theta, y by r by y by theta. That's a computation of the Jacobian, cos theta, negative r sine theta, r cos theta. Now you have to convince everyone that this matrix is invertible. Determinant test is a good test in this position. We compute the determinant of this Jacobian. That's the computation. We end up with r, which is non-zero every time except the one point where it is 0, the origin. And that's the test, which tells us that all we did before was legitimate workings. The inverse for the polar does exist according to the theorem on the previous slide because the Jacobian is invertible matrix. Yeah, so that's what I said here. F is locally invertible. When they say locally, that's what I told you earlier. When people invert functions, they don't really care about the inverse across the whole domain. Most likely, most often it never exists. But locally, around just particular point, it does. And this test tells you that around any point there is an inverse except the origin point where inverse doesn't exist. Where we don't know, as a matter of fact, whether the inverse exists or not, because the test doesn't work there. The second half of the slide just makes a direct computation of the derivative of the inverse via theorem. Look what it says. Let's just take a point, just any point, just randomly chosen point, root 2 pi and 4. My f value on this point is 1, 1, right? If you take it across here, angle pi and 4, radius root 2, yeah, it is 1, 1. So my Jacobian of the forward map of f map, that's a Jacobian right here. At this point, that's the computation. If I need to find now the Jacobian of the inverse map at this point, 1, 1, all I have to do, I have to invert this matrix. If I invert this matrix, gf of root 2 pi and 4, as a matrix, and we know how to do that. In case of 2 times 2 matrices, you have 2 ways to do it. One of them is a general way, which works for any matrix, via row echelon form. The other one, for the 2 times 2, you have a direct formula for the inverse. Either way will deliver the same answer, and that's the Jacobian of the inverse map. Right. We can double check this result in 2 ways now. One of them is that something I told you the other day. We can in fact present a direct formula for the inverse polar map. It's not an easy formula, but sometimes you can do it, and that's what the next slide does. Yeah, it gives you direct expression for r and theta in terms of x and y. That's the inverse polar map. However, it doesn't work everywhere. That's exactly what I'm telling you. Finding the inverse itself, it's not an easy task, and it doesn't exist everywhere. For instance, this formulae, they give you the inverse of a polar, but only within first quadrant. It's set right here. This formula doesn't work in the other quadrants. It's only the first quadrant inverse version. In the other quadrants, you have to alter your theta formula. But in the first quadrant, because the point from the slide before, this point, it's a point from the first quadrant. It's only bisector in the first quadrant. So for this particular point, we can use this formula for the inverse. And if I use that formula, I mean, for the direct computation, that's a Jacobian of the inverse map. It's harder to compute, but it's still computable, and it's actually interesting in light of the third linking. Or derivative of the root. Yeah, I agree with that. Derivative of this root by y, I agree with that. Tangent, inverse tangent function. Derivative is, well, there is a bit of the arithmetic here involved, but I tend to believe that this is true. And that's the Jacobian of the inverse map computed directly at the point 1, 1. It gave me the same value as before, as on the slide before. It's direct computation. Yeah. So once again, I'll tell you this. Remember that finding the actual formula for the inverse, it's not always easy task. Most of the time, it's not an easy task. But finding the derivatives of the inverse, given that all of the tests for the existence are satisfied, it's just the invertibility of the matrix. Actually, that's also not an easy task, but it's a computational task. I mean, it's the one which we have very strict and always working algorithm for. Yeah. Well, that's the one that's something I told you already, that you will have with this type of questions a few times, where you will need to find the fine approximation to the inverse map around the point. For that, the key ingredient is knowing the Jacobian, because that's the principal part of the affine approximation. And this Jacobian you can find either directly, like it is done here, or via the inverse map theorem, as in the slide before. But that's the affine approximation for this function. Well, I made this extra slide this morning because we can also link this inverse map theorem and what we've done right now with the inverse polar and polar map with our earlier computations. Computations we've done on week 3. I'll show you. It's the wrong one. How come I don't have this window? Fuzzy security. On week 3, we manipulated with the polar map we did in slightly different way, actually. I'll try to bring this in your memory. So back then we said, let's just take the inverse polar map, and I gave these names to this inverse map. Back then I didn't really stress much why we do have such an inverse map. Now we know we do have it, because when you compute the Jacobian for the forward map, which is the formula for the Jacobian, that's the same expression for the Jacobians we just saw on the main set of slides. Or we can actually express every component in the Jacobian in terms of x and y. That's how it is. Cos theta is just x by r. Sine theta is y by r. And these two, simply negative y and negative x. That's just alternative expression for the same Jacobian in terms of x and y and r rather than theta. If you compute this Jacobian, and that's another computation of the same Jacobian, it is r, and it is non-zero. Every time except the origin. And that's why we do have such an inverse. Now, when we show that such an inverse exists, on week 3, we saw another way to compute the partial derivatives of the inverse map, and by implication, the Jacobian of the inverse map, right? So this object, the Jacobian of the inverse map, now, but there was a third way to compute that. First one we just did today by inverting this matrix. It's this is by the inverse function theorem. Second one, there was again on the slide today when we just we found the expressions for these functions, explicit expressions, and we just differentiated them. It wasn't easy. They only worked in the first quadrant, but still it was sort of doable. The third one, as a matter of fact, should be the first one because we done it on week 3. I'm not going to bring this up, but I just bring the computations we come up back then. We did it twice. We did it by hand and with maple. That's the computations we come up back then for the partial derivatives of my inverse polar map. That's what we had back then. By earlier computation was a slide called Polar Substitution 1, week 3. Why did I bring this up? I brought this up for one reason. I want to double check this theorem of the inverse function once again. And now I want to double check it in the full generality for the polar map. I want to convince you that now if I multiply this matrix by this matrix, having this analytical formulae for every component of this matrix, both Jacobian of the P map and Jacobian of the P inverse map, polar inverse map, if I multiply these components analytically, I will see this relation that the one is the inverse matrix to the other. So if you multiply them, you will come up with the identity of size 2. Here's the verification. So if I compute this product, right, I have to take the row, first row here, dot product with the first column here. Here it is. XR times RX, X theta times theta X. If I sub in my analytical expressions, and I prefer to sub them in the form X and R, that's a substitution. And that is 1. XR for X on R by XR. Another X on R for RX from here. X theta from here, X theta is here, negative Y. And theta X from here, negative YR squared. If you compare this with the direct computations, when you had the direct formula for the inverse, there will be the same formula there. But the good thing is we come up with this without any help from knowing the formula for the inverse. And that verifies the first part, right? The dot product of the first row, first column is 1. This is a dot product of the first row in the second column. XR, X theta, it's the first row from here. It is X by R and negative Y here. X by R and negative Y. And RY and theta Y, it's from here. One value came from here and the other from here. It's 0. Another two lines, so to verify this identity. This is a product of second row here with the first column here. Y by R, it's for this YR, yes, right here. X by R, this is the, it is RY. Yeah, that's right. No, RX, sorry. From here. X is this component, and negative Y by R square is this component. And it is 0. Very simple arithmetic. And the final line, it's the dot product of the last row and the last column. And that should be 1. YR. It's YR is here. RY from here. And here we got X and theta by Y. That's right. Every time, of course, here, I mean, when you come up with this 1, we use the fact that X squared plus Y squared equal R squared. Yeah, that's 1. And that's another verification of the theorem on the example of a polar map. All of these different computations, they now come together in one single picture. Whichever one you use for your solutions, I don't really care much. Probably still the way we found this first time on week 3, it's a little bit specific, of course. The formula which is given to us by the inverse function theorem we discovered today, it's a more general way to do it. So first you come up with the Jacobian matrix and then you invert it the way you normally invert matrices, row echelon form or direct formula in case 2 times 2 matrices. That probably will be the best way to do it. Yeah. When you do your tutorial questions. Any questions? All right, I think the rest of the slides in relation to the inverse map They're all about the examples. It's another example. It's another example with the extra clause where you have to find the value of the inverse, approximate value of the inverse in a nearby point. You see in the point negative 1.2 and 2.1. For that, we expect you will use a affine approximation to find this approximate value. So the general scheme of the equation goes like this. First, you test that this function is invertible near the point of interest. The point of interest is 1, 0. For that, we need the Jacobian. That's the Jacobian of my function. Partial derivatives. Now, the Jacobian numerically at the point of interest, 1, 0 is like so. Now you test whether this Jacobian is invertible. It is actually, because determinant is here 2 take 4, negative 2. It is invertible matrix. Yes, you see determinant here negative 2, non-zero. It is invertible matrix, so we can come up with the Jacobian for the inverse map, even though we don't have the inverse map by itself. And actually this time, that just confirms what I said a few times already. Solving this in terms of, solving x and y, for x and y here in terms of the first component, second component here, I don't think you can do it analytically. Exponential functions combined with polynomials, this is never solvable analytically, Yet, the derivative of the inverse function, we know inverse exists even though we can't solve for it, and the derivative as simple as the inverse of the matrix, as simple as this. So when you need to present the affine approximation, I'm going to use this matrix. So my inverse function at uv point, this first two terms of the Taylor series expansion, that's what we call the affine approximation, the best affine approximation. The value of my f inverse at the point negative 1, 2, point of interest, which is 1, 0. It's a point of interest in the domain. And then the Jacobian, which came from here, and that's the whole expression. So if you need to know the approximate value at the point nearby, negative 1.2, 2.1, you just use these increments, negative 0.2 and 0.1. You use these increments across the affine approximation. That's the value. That's the value, they expect from us. Any questions? Right. If you don't have any questions, that's another result we need to know. It's the one which is called the implicit function theorem. It's very similar to, in spirit, it's very similar to inverse function theorem. It's when we can solve for the function given implicitly by an implicit equation. As with the inverse function, it's very often that you won't be able to solve it analytically, but finding the derivative of that function and predicting whether such a solution in principle may be constructed, this you can do. Yeah, we can discuss in the last 10 minutes. So this graph basically explains what's the main test for that. There are 3 points marked on this graph, 3 red points. Around this point, if you want to represent this curve as a graph of a function, that's how it sounds. That's how geometrically you will say it if you want to solve an equation. So if you have an equation gxy equals 0, for which you have a solution, this set of points, solving this equation for y, as algebraic statement, geometrically equivalent statement will be finding a function near this, for instance, this red point, such that the graph of that function will be exactly a piece of this blue curve. So around this red point, there must be such a function. Around this red point, there must be such a function for which this line, or this little piece of this line, near my red point is a graph. Around this point, it's no longer true. because my function cannot possibly have the graph which goes upwards. Or, as a matter of fact, around this point you have this line test failed, right? If you draw a vertical line, it will cross your blue curve near this red point twice, which means that this blue curve near the red point cannot be a graph of a function. And graph basically explains what happens, what will be the analytical test which ensures that the equation is solvable. The curve near the point should not be vertical. Curve being vertical, it's again some derivative test, some derivative being 0 or some derivative being non-zero. Yeah, it just shows you that well, these rectangles, I just explained the term near. It's another thing which is similar with the inverse function theorem. When you solve an equation, again, it's very little hope that you will be able to solve it globally. It's very little hope you will be able to find a function whose graph, this curve, in its entirety. Normally, we only hope to expect to solve the equations locally around the point. For instance, you see if you take this box around here, within this box there is no function. There is no such function for which this curve will be a graph, because again, the vertical line test failed within this green box. But as soon as you squeeze your box a little bit more, then you exclude these problematic points on the left-hand side, then you do have a function whose graph will be the blue curve within this smaller green box. That's a local nature of the implicit function theorem. You only can hope to solve something locally, but not globally. As much as it is true for the inverse function theorem. Inverse doesn't exist, most of the time it doesn't exist globally, it only exists locally. Well, here actually, no matter how much you squeeze your box into the point, your vertical line test will be failed all the time. Which means that around this point, there is no possibility to solve it even locally.
Sorry, what do you mean by graph exactly?
Graph?
Yeah.
What do you mean by graph?
So you keep saying, so that the graph will not exist or will exist. What do you mean by that?
Well, graph of the function is a collection of f of x points, right? So we'll just do it like this. If you have a function, f of x, right? So if you have a function like this, if you combine all of the points of this type, that's the graph, isn't it? If you combine all of the points of this type, your function may live on some omega or somewhere else. That's the graph. Okay? That's what we call a graph of a function, formally speaking. So when I say, if you look back at this slide, if you look at this piece of a line just within the within this green square, there is no way this piece can be reproduced as this set. Would you agree with that?
Yeah.
Because for this set to be reproducible, for the green line to be reproducible, shut up. The blue line to be reproducible as this set, this blue line must satisfy the vertical line test. You know what I mean? I mean, it's a vertical line test. I don't like this term, but I know you should be familiar with this term. Okay? That's exactly what I'm saying. No matter how small you make this green box, vertical line test will be failed all the time. So you won't be able to find this f function, no matter how hard you try, which will reproduce this blue line as this set. If you look back at the first point, if you look back at the point before, this point. For this point, if you take this section of the part of the blue line within this green box, again, vertical line failed. You cannot reproduce this blue line as the set on my dynamic slide. But you make it smaller and success. You can. I mean, in principle, you can. I mean, I can't give you the formula like sin x or something, but in principle, because the vertical line test works here. Whereas this point, no matter how close you go, it doesn't work. well, this graph, I hope you're getting this the distinction between the first 2 points and the second and the last one. And if you want to catch this difference analytically, that's what is called in the theorem. Well, actually, let me just scroll further to the theorem. Oh, too much. Did I miss it? Okay, I'll discuss. I'll take this slide to explain it to that. So this exercise we did with these 3 points, I hope it gave you the idea what happens when you can and when you can't reproduce this piece of a blue line as a graph of a function. But if you want to express this analytically, not just, well, yeah, if you want to express this analytically, here's how you do it. That's what should be satisfied for the g function in order for the line test to work. So, and that's actually the content of the implicit function theorem. It says you will be able to reproduce the blue curve, which is a solution to the equation g of xy equals 0. You will be able to reproduce that curve as a graph of a function, so you will be able to find some f which makes your blue curve of this structure if this condition is satisfied. It's very local nature of, it's a theorem of local nature, meaning that the theorem even doesn't tell you how close you have to go into the point in order to find the solution. But in principle, it says, yes, you will be able to do it as long as this condition is satisfied. As long as the partial derivative with respect to the y, with respect to the variable you're trying to solve for, is non-zero at the point around which you're trying to solve for it. Yeah. Any questions? Well, the next slides, they discuss actually the idea why this works, why this condition. It's the analytical equivalent of what we saw visually on the exercise with these 3 points, A, B, C, on the slide before. Next 2 slides, they try to explain why this works. What's the time? 5 minutes left. Well, the 5 minutes probably a little bit too little to discuss this. On the other hand, next time will be Wednesday lecture, which is 5 o'clock lecture. It's a tough choice, isn't it? Okay, probably we'll do it on Wednesday. Any questions? If you don't have any questions, I'd like to stop right now. We stopped 5 minutes before we should, which means that some other day I may claim this 5 minutes back. If I'm late or something, hopefully that won't happen, but it might happen. Anyway, thank you very much. I'll see you all on Wednesday.